associated with 79 is 3 because you're counting 79 and 64 and 83. And the subtree size associated with 49 is 5, okay, because you're counting everything underneath it. How did we get these numbers? Well, you want to think about this as you started with an empty set and you kept inserting into it, and you were doing a sequence of insert and delete operations. And if I explain to you how an insert operation modifies these numbers, that is pretty much all you need. And of course, analogously for a delete operation. All right? So what would happen for, let's say you wanted to insert 43. You would insert 43 at this point. And what you do is you follow the insertion path just like you did before. But when you're following that path, you're going to increment the nodes that you're seeing by 1. So you're going to add 43 to this. And you'd add 5 plus 1 because you see 49. And then you'd go down and you'd see 46. And so you'd add 1 to that. And then finally, you add 43 and you assign, since it's a leaf, you'd assign the value corresponding to the subtree size of this new node that you put in there to be 1. All right? It gets a little teensy bit more complicated when you want to do the k-minute check. Okay? But from a complexity standpoint, if you're not worried about constant factors, you can just say, you know what? I'm going to first run the regular insert, ignoring the subtree sizes. And if it fails, I'm done, because I'm not going to modify the BST, and I'm done. I'm not going to have to modify the subtree sizes. If it succeeds, then I'm going to go in, and I know now that I can increment each of these nodes because I know I'm going to be successful. Okay? So that's sort of a trivial way of solving this problem that from an asymptotic complexity standpoint gives you your order H augmented insert. That make sense? Now, you could do something better than that. I mean, I would urge you, if you wrote something that we asked you to write something like this, to create a single procedure that essentially uses recursion appropriately to do the right thing in one pass through the BST. And we'll talk about things like that as we go along in sections and possibly in lectures. All right, so that's the subtree insert delete. Everyone buy that? Yeah, question back there. Yeah. Well, what you'd have to do is bubble up pointers. So you'd have to actually have 64 connected to. What will happen is 83 would actually come up, and you'd essentially have something. This is not quite how it works, but 83 would move up, and you'd have 64 to the left. That's what would happen for delete in this case. Okay. So you'd have to move pointers in the case of delete. All right. And we're not done with binary search tree operations from a standpoint of teaching you about them. We'll talk about them not just in today's lecture, but later as well. All right? So there's one thing missing here, though, which is I haven't quite figured out. I've told you how these subtree sizes work, but it's not completely clear. This is the last thing we have to do, is how are you going to compute rank T from the subtree sizes, right? And so everyone understands subtree sizes? It's just the number of nodes that are underneath you, okay? And you remember to count yourself, all right? Now, what is rank T? Rank T is how many planes are scheduled to land at times less than or equal to T, all right? So now I have a BST structure that looks like the one I just ended up with, okay? So I've added this 43, and so let me draw that out here and see if you can answer this question. This is a subtle question. So I got 49, and that subtree size is 6. I got 46, subtree size is 2, 43, 79, 64, and 83. Okay? So what I want is what lands before T. All right? And how do I do that? Give me an algorithm that would allow me to compute in order h time, I want to do this in order h time, what lands before t? Someone? Yeah?
So first we would have to find where to insert it like we did before.
Right, right.
And then because we have the order of whatever was before, not the order, like
the sizes, yeah.
And then we can look what's more than it on the right, we can subtract it, and we get...
What is more than it on the right? Do you want to
Because like the
okay.
bigger one is on the right.
Right.
And then we can take this minus this and we get...
What's left? That's great. That's excellent. Excellent. So I'm going to do it a little bit differently from what you described. I'm going to actually do it, sort of a more positive way. No offense intended. What we're going to do is we're going to add up the things that we want to add up. And what you have to do is walk. Your first step was right on. I mean, your answer is correct. I'm just going to do it a little bit differently. You walk down the tree to find the desired time. Okay? This is just your search. Right? We know how to do that. As you walk down, you add in the nodes, that is the subtree sizes. You're just adding in the nodes here. So if you see, depending on the number of nodes that you see, as you're going deeper in, you want to add in the nodes. And you're going to add 1 to that, corresponding to the nodes that are smaller. And we're going to add in the subtree sizes to the left, right, as opposed to subtracting. All right? That may not make a lot of sense, but I guarantee you it will once we do an example. So what's going on here? I want to find a place to insert. I'm not actually going to do the insert, but think of it as doing a lookup. And along the way, I need to figure out the less than operator. I want to find all of the things that are less than this value I'm searching for. And so I have to do a bit of arithmetic. So let's say that I'm looking for what's less than or equal to 79, right? So t equals 79. So I'm going to look at 49. I'm going to walk down. I'm going to look at 49. And because I say I'm looking at 49, and the 49 is clearly less than 79, so I'm going to add 1. And that's this check over here. I move on, and what I need to do now is move to the right, because 79 is greater than 49. That's how my search would work. But because I've moved to the right, I'm going to add the subtree sizes that were to the left. Okay? Because I know that all of the things to the left are clearly less than 79. Okay? So I'm going to add 2 corresponding to subtree 46. Right? So I'm not actually looking there, but I'm going to add all of that stuff in. I'm going to move to the right, and now I'm going to see 79. At this point, 79 is less than or equal to 79, right? And so I'm going to see 79, and I'm going to add 1.